look at the title first. The title, Optimality of Algorithms. In this part, the main concept we will learn, optimality issue. If our algorithms are optimal or not. Another important question. Yeah. D.1, minimum selection problem. We start with a simple problem first. Then we use this problem to study the optimality question. All right. First, let me give you our problem number 4. Find the minimum number. Find the minimum of an array. Yeah. So we are given an array. Yeah. The array is unordered. Yeah. If we do not say anything, if we do not say it is ordered, then we assume it is unordered. Find the index I such that A of I is the minimum of the array. That's a simple problem. Minimum of the array. I think every one of you can solve it easily. Right? Of you can solve it easily. Just the one for loop, you can solve it. But the main issue is not at the solution. The main issue is at if your algorithm is optimal or not. That's the key issue here. Yeah. But first, let's look at the solution. Yeah. The problem type, we have our second problem type. The first type, search type. That's the first type. Second type, this type we call selection type. You select the minimum element in the array. Selection type question. Selection type. Yeah. So here, let me give you the general selection problem. Yeah. We will do several selection problems in this class. The general selection problem. Yeah. Find the kth smallest. You can change that k number, the first, second, third, any k number you want to use within the range. Within the range, find the kth smallest element in a given array. That's the selection problem. Okay. The minimum, find the first smallest element. Yeah. It's a special selection problem, and it is easiest selection problem. Yeah. K equals 1. Yeah. The reference textbook. Yeah. Now let's do the analysis. Solving this question, pretty straightforward. Yeah. Yeah. First, let us do initialization. When we start, we create a minimum variable, min variable, min. We assign it as the first value of this variable, initial value of the variable. Min equals A of 0. So we start to comparison from the first one. Yeah. All right, the first assignment. It's an assignment operation. Yeah. Another, yeah. Here, assignment operation, basic operation. The general step, next, we compare min and the current element, A of I, current. We do a for loop from 1 through n minus 1. Yeah, the current, we do comparison, compare min with A of I. If min is greater than A of I, we replace min by A of I. We make it smaller. We find a smaller element, so we should update the value of this main variable. Yeah. Another assignment. Here you can see. This is a comparison. This is assignment. Two operations. Two basic operations here. Yeah. All right. Otherwise, less than or equal, we do not do update. Yeah. We just go to the next iterations. Yeah. Oh yeah. After that, we go to next iterations. Compare main and the next element in the array and until we reach the last element. So you do things like this. Comparison, assignment, if necessary, right? Until you reach the last element, then this variable should hold the minimum value of the whole array. That's the solution part. The solution part, straightforward, easy to understand. Yeah. Nothing to talk about here. Yeah. Nothing special to talk about. Yeah. But here, probably I can ask you a few questions. Yeah, here, just return it. Yeah. Yeah. Here we want to look at the number of comparisons, efficiency numbers. Yeah. All right. N-1 comparison, right? Yeah. Because the first one, it's an assignment. Here I ask you number of comparisons. I do not ask you assignment. All right? Yeah. Assignment depends, right? Yeah, it's hard to tell. Yeah. It depends on the location of the minimum, right? You don't know the location of the minimum. So you may not know how many assignments. But for the comparison, you know, except the first one. First one, you do not need to compare with anything. First one, just one assignment. After the first one, for each remaining element, you need to do one comparison. So that's why you need to have N-1 comparisons for this algorithm. Yeah. Yeah. Now you may like to ask best case, worst case, average case, same number. Because that's only one case you have. So it is the best case, it is the worst case, it is the average case. That simple. Okay? Only one case. No. All right. But there is the next question. So now we need to come to our key question here. Is it possible to further improve the algorithm? That question. Yeah. A value polynomial, remember, before we have the Horner's rule, we have one evaluation method, but not good, so we can still improve it. So here we want to try to improve this basic algorithm. So we need to answer this question. Yeah. Two possibilities for this question. Yeah. First, improve the algorithm. You can improve it. Yeah. You find a way to improve it. That's the first option. But second one, you cannot improve. Yeah. You try very hard, but you couldn't solve it. You couldn't make it. So, but the next thing you can do, convince people that it is already optimal. The current algorithm is already optimal. Nobody can improve it. That's the main topic of this part, optimality. So here we need to look at the optimality issue for this simple algorithm. Is it already optimal? Yeah? Yeah. Okay, yeah. It looks not that easy. The optimality looks not that easy. Yeah. Why it is hard? Why it is relatively hard? The harder part is, among all the possible algorithms, how to show that this one is optimal, right? Because in order to show this algorithm is optimal, you need to consider all the possible algorithms solving this problem, right? You need to consider all the possible, all the algorithms. Now, so that is hard. How can you consider all the possible algorithms solving this problem? We don't know, right? We don't know how many different algorithms in the world that can be used to solve this problem. Nobody knows that. So that's the hard part. Yeah. All right. But we need to find a way to do it. Here, including unknown algorithms. Many algorithms are unknown. Excuse me. People have not developed those algorithms, right? Unknown algorithms. But you need to consider unknown algorithms. How difficult it is. Right? But we can. There is a way to do it. We can. How do we convince people that our algorithm is optimal? Here we need to make convincing arguments. Convincing arguments. All right? We need some imagination based on our real world experience. We need to make a story. The story is based on real world experience. Everyone has that experience. Okay, you're familiar with that. So we use that story to go through this question carefully and convince people this is the best that people can do, not just we, everyone can do. No exception. Everyone can do, not just us. Because if we say us, we may not be very smart. There are many other smarter people than us, than we, right? Than we. So here, what we want to show, no matter how smart you are, you cannot do better than this. Nobody can do better than this, no matter how high your IQ is. That's what we are going to do. Okay? All right, so look at the story. We count the number of comparisons. Okay? So this is our main object to study, comparison object. We study this. All right. Now, we want to associate it with the real world object, match or game. In sports games, people play matches, right? Each other, opponents. So one player wants to beat another one. Okay? So here, can we use that activity for comparison? They are similar. Player A beats player B. We can treat as player A is greater than player B. How about that? Or less than. Actually, why less than? Because here we are looking for the minimum. Minimum means the smaller the better, right? The smaller, that means the winner. The smaller elements wins the game. How about that? That story. Smaller element wins the game. So the player with smaller, some measure, okay? Points, losing points, is the winner. So comparison. We use comparison and sports game match between two players. The winner corresponds to the smaller element or smallest element. That story. All right, between two players. Now, less than, A less than B, the winner. The element, that is less than the other one, the less one, that's the winner. Okay? Wait. Equal, tie, greater than, lose. Yeah, greater than lose. But we may eliminate the tie case. Yeah. Because in this one, yeah, tie or we put together tie and lose because you are not the winner, so we just skip it. Skip. Okay, tie and lose. We put in the same category. Yeah, not a winner, so we pass it. Yeah. Now next, convincing argument. When we connect to some sports game, then we can make our convincing argument. Yeah. Here I use a list of arguments. Yeah. So try to follow the logic. See if it is convincing. If it is convincing, follow the logic. Okay. Remember our goal, n-1 comparisons is the minimum. Nobody can use n-2 comparison to find the minimum. Okay? n-1, the absolute minimum. Yeah. That's our goal. All right, here, let me make the convincing argument. Yeah. First, imagine that min is the final winner, the minimum. Yeah. The final winner of the whole game. Yeah. There are many players that play together, okay, each other. The final winner, minimum. All right? Yeah. Then, that winner needs to beat all the other elements or players in the array through comparison, directly or indirectly. Here, directly, indirectly. Directly, we know the meaning. A beats B directly, direct comparison. That's direct. What do you mean indirect? There is an indirect comparison. A and B, they do not do comparison directly, but there is some indirect way to do comparison. Let me show you the example. Indirect way. Okay? Yeah. All right. Yeah, here. Yeah. All right. Okay? Yeah. Yeah, let me do here. Yeah. Suppose A greater, yeah. Here, remember, we use less than. A less than B and B less than C, then we have A less than C, right? In math, we call it transitivity property. A less than B, if we know A less than B and B less than C, then we automatically, we have A less than C. Yeah. Here, look at, suppose there are players, 3 players, A, B, C. A beats B, B beats C, then A and C, we do not need them play, right? Yeah, based on our rule, we know, based on our rule, A automatically beats C. So we call it indirect way beat. No game between A and C because A beats B, B beats C, based on our rule, yeah, math rule. Yeah, not necessary in the real sports game. In real sports game, not necessary, right? Yeah, but here, although we use that story in our real life, but not 100%. Yeah, but we need to follow the fundamentals in our algorithm and our math, arithmetic rules, right? This is the arithmetic rules, math rules, so we have to follow, okay? All right, so here, that's the indirect way, okay? Indirect way, yeah. All right, so the winner has to beat everybody else directly or indirectly. Do you agree with this statement? Yeah, even indirectly has to beat that person. All right? Otherwise, how can you claim you are the winner? Yeah. How? You cannot claim you are the winner. Because there is someone you do not know if you can beat that person or not. Nobody knows. How can you claim you are the winner? Yeah. So that's another argument. Yeah. Next argument. If an element loses once, it is eliminated. Yeah. Because we don't want to play extra games. Because if one element loses to a player, that element cannot be the winner, right? Our goal is to find a winner. We don't want to find the, runner-up, right? Second, third, fourth. We don't want to find those other players. We only want to find the absolute winner. So one player, if that person loses once, we eliminate it. Yeah. Because in this way, we can reduce the cost. Okay, we can reduce the cost. We do not do unnecessary comparisons. Yeah, so that's another argument. Next argument. Each comparison can only eliminate one element. How about that? One comparison can only eliminate one element. Can you use one comparison to eliminate two elements? You cannot, right? Between A and B, one beats another one, the loser get eliminated automatically. Yeah, but only one loser gets eliminated. Yeah, so each comparison can only eliminate one element. Yeah. Next one. We need to eliminate n-1 elements. Right? Yeah. Because at the end, only one winner left. The remaining n-1 elements all get eliminated. Right? Look at that. We need to eliminate n-1 elements. Thus, we need at least n-1 comparisons. Yeah? Yeah, because one elimination corresponds to one element, right? One comparison corresponds to one eliminated element. How about that? One comparison corresponds to one eliminated element. But now we need n-1 eliminated elements, so we need at least n-1 comparisons, right? We need at least n-1 comparisons. Otherwise, how can you eliminate n-1 elements? One comparison, you can only eliminate one. But there are n-1 elements to be eliminated. So the best you can do using n-1 comparisons to eliminate n-1 elements, right? That's the best you can do. Why I say the best you can do? Because sometimes people may do some redundant comparison. You waste your comparisons. You do redundant, so that comparison useless. It does not provide any helpful information, so you waste it. So that's the redundant comparisons, unnecessary comparisons. That's possible. That's possible. Yeah. So that's why we say at least n-1 comparisons. The minimum number of comparisons you need n-1. And then nobody can beat that. How about that? Nobody can beat that. Nobody can do better than n-1 comparisons. How about that? Is that convincing? Look, let us combine all these arguments. Do you think it's enough to convince people? Yeah. Yeah. And, yeah, because we have the solution. with exact n-1 comparisons. So that means our solution is optimal. We have it. Other people cannot do better. We have one that delivers the best performance. How about that? That argument. All right? That argument. Convincing? Yeah. So I feel convincing. There is no hole here. There is no hole. The logic is perfect. Our conclusion, this algorithm is optimal. Optimal among all the algorithms solving this problem, including those unknown. Do you agree? Including those unknown. There are some unknown algorithms. No matter, even unknown, we don't know those algorithms, but our argument is good enough to cover those unknown algorithms. How about that? Yeah, we make it. We cover unknown algorithms. How about that? Is it possible? So think about this. Is it possible we can cover, we can describe properties for unknown algorithms? Think about this. Is it possible we can study properties for unknown algorithms? Is that possible? We study properties. Here, we study properties for unknown, containing unknown algorithms. How about that? The answer is yes. We can study unknown algorithms. We can study unknown algorithms. If we can find some common property that is shared by all unknown algorithms, we can study them. But we need to find some common property that is shared by all those algorithms, no matter known or unknown. If we can do that, you can study unknown algorithms. Can you understand this point? A little abstract. No? Because if people try to understand this, use their intuition, they may feel hard. For unknown, you do not know the details. How can you study those things? Yeah, we have the limitation, but at least we can study in some way if we can find a property. So here we find a property, common property, shared by all those algorithms. That means one comparison can only eliminate one element. That's the common property, no matter it's known or unknown. How about that? Is that a common property? One comparison can only, at the most, eliminate one element. No more than that. That's the common property. No matter it is known or unknown, you have to follow this property. All right? Yeah. The reason I emphasize this point is because later we have another big situation. We need to use this logic. Another very big situation. We need to use this logic. That is when we study sorting. Sort, the third basic type of algorithms. Search, selection, and sort. The third one, sort. When we study sort, there is one very important topic, that is the minimum number of comparisons to sort certain number of elements. Later we will get there. We will get there. We want to study what is the minimum number of comparisons to get one array sorted. That's a difficult question. Difficult question, very challenging. Yeah. But here, when we study that, we need to consider all the unknown sorting algorithms, right? Yeah. The minimum, you should cover all the sorting algorithms. And we know many of them unknown. Yeah. Many of them unknown, but we can still study them. We can still study unknown because we can find a common property shared by all the sorting algorithms. Just like what we can do here. Common property shared by all those algorithms. Yeah. So here I just give you some mental preparation for that sorting problem. Okay? Yeah. Very challenging. Yeah. Related to the sorting, yeah, here I can throw out one extremely challenging sorting question. If you want to try as a puzzle, you can try. Okay, puzzle. Sort 5-element array. Given an array with 5 elements with different values, do not consider equal case. Okay? Yeah. Usually we want to make the case as simple as possible. 5 elements with different values. All right. Now we want to do comparison to get them sorted. Yeah. Ascending order. Okay? Ascending order. What is the minimum number of comparisons to sort 5-element array? So if you find that number, you need to really sort it. For example, if you say 7, then you need to really find a method using just 7 comparisons to get it sorted. Yeah. The answer is 7. Yeah, the answer is 7. But extremely difficult. Yeah, if you want to try, keep in your mind, it is extremely difficult. Although it's just 5 elements, small number, 5 elements, okay, small number. But using 7 comparisons to solve it, extremely difficult. Okay, yeah, at some point I will give you the solution. So if you want to try just as a puzzle, mental, challenging puzzle, yeah. So you can try it. Yeah. But I will give you the solution later. Yeah. All right. So next topic. All right. Yeah. Here, in this topic, I want to point it out another very important method we use, elimination method. Here, we do elimination. Yeah. Look at that. We do elimination. Yeah. So here we want to take it out, elimination method, because later, in many situations, we need to use elimination method. Many situations. Yeah. Elimination method. Yeah, very powerful. Very, very powerful. Okay? Yeah. Here, this is our first view of elimination method. Yeah. All right. Okay? Yeah. The idea is so simple, very straightforward. Try to eliminate as many as possible elements. So based on the given conditions, you try to eliminate as many as possible elements in the array. It looks like nothing, right? It looks like nothing, but actually it's important. People do not realize to do that. People do not realize to do that. Yeah. Yeah. So you will have the similar situation of that. Let me give you an example. Let me give you an example. All right. Why people do not realize that. Okay. For example, if we want to sort 5-element array, if after a few comparisons we already know there is a top one, there is the biggest one, okay? We already know it. We can eliminate from the consideration. Then we reduce the array size, right? So the 5-element array after elimination, it becomes 4-element array. So that's the elimination method. But usually people do not realize it. After they do comparison, they find the top one, the largest one. They do not realize they can eliminate it. They still consider 5-element array. Still do a lot of redundant work. You know, that's something related to this elimination method. You really need to keep in mind when you have some conditions, if you can apply the condition to eliminate a few elements, you should do it to reduce the problem size, to reduce the number of elements to be considered. The smaller number of elements to be considered, the easier the problem, right? So that's the essence of elimination method. You want to reduce the problem size after elimination. Yeah. So later I will give you a lot of details, many examples, showing you how effective is this elimination method. Yeah. All right. So let's move to the next topic.